Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Ashley Villar with us today. Hi, Ashley.
Hi, thanks for having me.
Oh, well, thank you for agreeing to talk about your really lovely APJ supplement article. It's a nice one.
Yeah, thanks.
Ashley, where are you located at?
So I'm in State College, Pennsylvania, which is location of Penn State University. Yeah, I just started here as an assistant professor in July.
Oh, well, congratulations.
Yeah, thank you. Yeah, fun adjustment. Yeah.
Yeah, it's an adjustment.
Yeah.
Very good. Very good. I do have to remark because I keep staring over your shoulder there. I think that's a really awesome board over your thing. We have integrals and we got dot products and we got all kinds of things going on over there. Probabilities, it looks like. It's fantastic.
Yeah.
So you're in a very suitable environment for talking about what we're going to talk about when we get to the article.
Yeah, it's unfortunately is not my blackboard. It says do not erase. So I'm in a temporary office. And Dongwei Zhang, who's normally here, is on sabbatical. So I'm protecting his board.
Yeah, good job. That is awesome. So I take it Penn State is back in person?
Yep. Classes are largely in person. We are encouraged to come in with our door shut. Okay. Yeah, but we're really hoping things get back to normal, but we'll see.
Indeed. So are you teaching here in your first semester?
I'm not teaching, which is nice. Yeah.
Very good. Very
cool. Yeah. I don't have to teach until spring.
Very good. Let's see. How was the summer in Penn State?
It's great.
Great.
Yeah, I was in
you win a prize for saying that or something.
I know. Well, I was in New York City for my previous job at Columbia. And I lived in a less than 300 square feet apartment. And so the move here has just been all around enjoyable.
Okay.
So summer, I think, is beautiful.
I enjoy the weather more when I have more space, let's say.
Yeah, exactly. It's been nice. Yeah.
Very good.
Yeah.
Let's see. We're going to start a 4-day rain period here in Phoenix. I was just looking out the window. We're a little cloudy today on this August 30th of 2021. So our Phoenix temperature will be a little bit down, but Phoenix, we are not out of the summer yet. We will still blast as we come into September. So
yeah.
So Ashley, what do you like to do for research?
So I study extragalactic transients. So that means things which evolve on human timescales. In particular, I think about the explosions of massive stars, so core collapse supernovae, but also other explosions like kilonovae, which is the electromagnetic counterpart to neutron star mergers. And I think about this in the context of big data and machine learning statistics. So what do you do when you see lots of these explosions, and what can you learn about the progenitor population?
Very cool. Very cool. And that is going to lead us very naturally into this lovely APJ supplement article.
Yes. A
deep learning approach for live anomaly detection of extragalactic transients. And Ashley, take us away.
Yeah, so I'll step back and explain where we are right now in the field. I think time domains are a really fun place where we're really entering this era of big, quote unquote, big data. And so by that, I mean the discovery rate of, let's say, supernovae as a catch-all for transients has been growing exponentially since the 80s. And that's really been driven just by new instrumentation that allows for these wide field untargeted surveys. So we look at large parts of the sky every night or every few nights, and we look for new stars or new explosions. So in the 80s, we found dozens per year, and that's been growing. So now we find about 10,000 per year, which is a very hefty number. But in a few years, from what I understand, now it's the start of 2024. LSST, so the Vera Rubin Observatory, is going to be commissioned and come online. It's going to start something called the Legacy Survey of Space and Time, or LSST, that will run for 10 years. And that is expected to have an annual discovery rate for supernovae of over 1 million. And so it's this really fun period where we're actually breaking exponential growth, and we're going to have this 2 orders of magnitude increase in discovery. Yeah. So that's very fun. And there's lots of questions that kind of open up there. And I think one that's really interesting is this idea of we really only have human timescales to study these explosions. They only are visible for month to month, some as short as a week. And so there's this decision we have to make in real time of, well, what do we look at? And a fun number I like to think about is, let's pretend that just, given human hours that we have in the world, and also multi-wavelength resources we have, I would say at most we follow up 100 transients a year, and that's pretty generous. And so 100 in a million is a like 1 in 10,000 level of importance. And so we have to start making the decision that's equivalent to, if all scientists agreed that we had to study one event in 2020, what would it have been? And why is it reached that level of importance to our field? What is it driving forward in our knowledge? And we have to make this decision every day, basically, with LSST. And so the idea of this paper is really, I think it's not, and I think many people agree, it's not ridiculous to think that LSST is going to discover something new. This happens all the time in astronomy, especially time domain. Yeah. And so there's this question of, how do you pick out these kind of needles in the haystack of events in real time that are quote unquote worthy of follow-up? And in this case, we're specifically thinking about a physics agnostic approach to find the unknown unknowns. If something new happens, can we identify it early and trigger follow-up? And that's what anomaly means in this context. Cool. So that's what this paper is exploring, is, okay, given this kind of new world of so many transients to choose from, how do you actually choose, or how do you detect new physics without knowing exactly what you're looking for? Yeah.
I just wanted to make a comment there on your exponential growth. There was a period of time when the alphabet was transients. We had 87A, we might have BCD, and then we started getting more, and so then it was a double alphabet, and we're into the triple alphabets. And by the time you get up to 1 million, I think we might want to reconsider the classification system.
Yeah, it's wild right now. I think it's funny to me that we're at the point where we really should be filtering for certain words, because we can make 6-letter words now. And
I know. Telephone number at that point.
I definitely,
Anyway, that's a side thing. I didn't mean to sidetrack you.
Oh, no, that's very true. There's a lot of just funny human aspects to this growth. And that's definitely one of them. I think that's everything I want to say about the background. So we can go to the first figure.
Let's go to figure 1. Where's light curves? Okay.
I think it's thinking slow. Oh, there it goes. Okay.
Drag. Okay.
Yeah. So I think, so a lot of this paper, it's almost funny that it's physics agnostic. So I think a lot of this is about statistics and machine learning. So for this paper though, I was so lucky that I could rely on the community for this really wonderful simulated data set that's called Plastic. And it is a community effort that was led by Rick Kessler, Renee Holchek, Gautam Narayan, and many other people. And what it is an attempt to be an LSST simulation for variable objects, where they asked the community to donate as many models that we could think of, theoretical and observed. And originally it was purposed as a classification challenge. So given the data, can you sort it into different buckets? So we are repurposing this data to instead say, okay, given data without labels, pretend it's just real incoming LSST data and we don't have spectroscopy on everything. Can we find weirdos?
Yep. Okay.
Okay, so that's where this data is coming from. It's all synthetic, but it is meant to be as realistic simulation of LST as possible. And so this figure is showing just an example of a few light curves where I know the label, which is what's given. And I think it's a really nice representation of just what a weird data problem this is. And in particular, so transients are obviously, they're aperiodic, they're terminal, they kind of happen for a set duration and they disappear. And that time scale is pretty variable, like I said, weeks to months. And they're also not observed in the same filter every night. And so if you wanted to study one supernova, you could imagine that, like, ideally, you want to know what every photon at every wavelength is doing at every moment in time. Right. And that really is telling you about the underlying SED, which directly connects to whatever engine is driving it. Mm-hmm. The reality, of course, is that we very sparsely sample that. So we grab it at different wavelengths at different times, and we have to build a complete picture from that.
Yep.
It's really hard to work with data like this because you can't find a simple feature space to explore. In other words, I have to figure out, okay, do I want to measure how bright these things are and in what filter? Do I want to measure how long they last? It's unclear. And so this figure is showing kind of our first step of what we need to take care of is we need to take care of the fact that these are irregularly sampled and kind of sparse light curves. And so the way we do that is through something called a Gaussian process. And for this talk, the only relevant part of that is the fact that it's a 2D interpolation we do. So we say, okay, I know that all the filters are coming out of the same, let's say, black body SED. And so I know they should be correlated, both in time and wavelength space. And so what we do is we kind of enforce that correlation and we do the interpolation based on that enforced correlation. And that's why we see these nice light curves that they don't exactly track one another, but even in the case of totally missing data, like that middle panel, you can still have some realistic guess of what the flux is doing as a function of time, and you get a realistic uncertainty on that flux that may be very high. And I say flux, this is magnitude here.
Yeah, understood. Yep.
So this is taking care of our first problem, which is that the data is hard to work with in that it's irregularly sampled and kind of sparse.
Yep.
Okay, so now our goal is we have all of these light curves and we want to find weirdos in it. And we want to be able to do it somehow in real time. And I want the next figure highlights what weirdos might mean. So in the plastic data set, we have all the labels because it's simulated. And so I can ask the question of what it is. We're going to train this algorithm to look for weirdos without telling it what everything is, because that would be cheating. But it's good to know that because this is a realistically generated survey, the universe doesn't make things equally. It's very biased. And there are very common classes, type 1a being the most common, and there are very uncommon classes, both for just being intrinsically rare and very hard to observe with this type of survey. So like kilonovae, which I think there's only 2 kilonovae or something in this whole simulation. Okay. And they're pretty poorly observed. And so what we're going to do is we're going to say, okay, I am going to figure out a weirdness score for all of the transients that I have, and I want to find the weirdest ones. And then I'm going to check my answer to see if the ones that are really weird really are from the minority versus the majority classes.
Okay.
Okay, so the next figure is kind of the figure that explains everything.
All right.
Yeah.
Let's go. Okay, there's your interpolation using the GPs. Light goods. That's your score. That's your weirdo score, right?
That's my weirdo score, yeah.
Weirdo score, people. But I like that descriptor. It's very nice.
Yeah.
Yeah. All right. Yeah, we got a mini shot here. This is
I can explain more what it means.
Okay.
So this is it. This is the whole algorithm we present. It really is. It's easy to summarize, but a little complex in details. So I'll spend some time on this. So we talked about the first part, which is this idea that we need to figure out some way of extracting features that we can compare the different supernovae to each other. And in particular, we really want the number of features to be small. And the reason why is because we're going to use whatever feature space we think of, we're going to use it to search for those anomalies. And the larger and larger dimensionality that space has, the sparser and sparser it'll be. And so we really want it to be a nice dense feature space that we can very easily apply cuts to. We also want it to be big enough that it represents kind of all the natural variability we see. So there's a little bit of an art to choosing that. In this case, I think we just chose 10, which is based on previous studies, it's about the number of free parameters you expect in supernova-like models. So it's kind of not too big and it's not too small.
Right.
Okay, so all of that is this. So let me explain how we actually now extract those features from every light curve.
Okay.
And that's step 2, which is kind of the meat of this. So we have these interpolated light curves, which you can think of as translating them just into matrices, where I'm showing on the left-hand side of 2. Every kind of column of this matrix represents one data point in time, where for every time I either have observed G band, R band, something, and then I've interpolated the other ones. So at every point I have some guess or measurement of UGRIZ observations.
Okay, I'm with you.
And I also have their uncertainties. So now my column vector is the measurements, the uncertainties, and I have one more important piece of information, which is the phase. And there's lots of ways you can interpret this. The most physically obvious is how long after explosion, but we don't measure that. We instead, an easy measurement is the peak luminosity. So we just say, okay, relative to peak luminosity, I'll call that the phase.
Okay.
And so we have lots of these columns that each represent a point, a phase in time, and all of the estimated flux.
Yes.
So our job is to take this kind of large matrix of arbitrary size. It can be lots of time observed, a little time observed, whatever, and find some representation of it. So like a model that we can use to look for weirdos.
Okay.
And so I like comparing this to a model because I think that's a really easy way of explaining this. So for example, if I actually fit a physical model, I might describe a supernova based on its how much mass is ejected and the energy. Okay, and then I could say something, okay, now I have mass and energy, and the different types would cluster in different areas. I'm doing the same thing, but I'm not imposing a physical model. I'm just saying, I'm going to use a neural network to figure out what that scientific model is for me.
Okay.
And the way you do that is you build something called an autoencoder. An autoencoder has a simple job that it is going to take your input matrix, my nice light curve picture, and it's going to try to give out the exact same picture. And this sounds kind of silly because I think a really easy way of doing this would be multiplying your input by 1, and then you get the output perfectly. And so that's obviously not a useful encoder in that it doesn't really give us these model parameters. So instead, what you do is you say, well, I'm going to train a series of matrices with different element values, so weights in them, so that they will shrink in size through these multiplications, and they will crunch this big matrix of values, the light curve, into just 10 numbers. And then I'm going to start with those 10 numbers and allow it to expand back out to the light curve. But those 10 numbers need to contain all of the information of my light curve, which might be hundreds of kind of data points.
Okay.
That's that idea. And in particular, we use a special kind of autoencoder. Well, there's 2 special little bells and whistles to it. The first is that it's recurrent, which just means that as new data comes in, we can update this encoder. And so it gets a better and better idea of, okay, I think actually the supernova looks like this type. And so I'm gonna tweak what I think it should look like. And then the second thing we do is it's a variational autoencoder. And that means that instead of learning 10 numbers that represent the entire light curve, I'm also going to learn the uncertainty on those numbers at the exact same time. So it's very closely equivalent. It's pretty closely equivalent to the idea, again, of learning, oh, for this supernova, I'm learning an ejecta mass and an energy, and then how uncertain I am. The difference is, of course, like you should not assume that these are physically meaningful. They're just useful features. and their uncertainties.
Very good. I'm with you.
Okay, great. Okay, and then what's kind of nice about this model is that we're able to, it really is like a function in that we can input any times we want, and then we can output any times we want. And so I can even interpolate and extrapolate this light curve if I want to. We don't really use that for this study though. Okay, so now that I have passed every supernova through the autoencoder, I've taken all of their messy light curves, and now instead, for the million supernova I have 10 numbers that describe each one of them. I also have the uncertainty of those 10 numbers. And so now I have this really nice vector space, so it's called latent space, that I can now do weirdo detection in, anomaly detection on. And because we made it variational, it wants to cluster as much as it can. It wants to look like a Gaussian. And if it won't, it's because you're weird and you can't fit in this Gaussian.
Okay.
Yeah, so that's the idea. And so the step 3 now is we use an algorithm to look for, we take every supernova, we plot it in this space, that's kind of this dark cloud. And that's where most of the supernovae are. And then I've highlighted in the purple stars, those are ones that just aren't clustering well in this space.
Yes.
So I will mention that this is specifically called out of distribution anomaly detection. I have forced all my supernovae to sit in a distribution, and I'm looking for ones that don't fit in it. And so I'm only sensitive to anomalies which look different in this learned latent space, which is just to say, in this weird model, my neural net learned, they don't look like everything else.
Right.
Okay, so to actually look for the anomalies, once we have this nice latent space, we use something called an isolation forest, which is, so it sounds like it's a series of decision trees that are literally just asking in this learned latent space. So here's just a 2D, right, representation. I have this vertical line that's just asking, okay, am I left or right of the vertical line? And I'm going to now separate the left half. And now I'm just going to make another cut on the right half, and again, make a binary cut and do it again and again and again. And the idea is that if I can separate you in one cut, you look really weird. You look like the weirdest guy in here.
Fair enough.
Okay. Yeah. But if it takes more and more and more cuts, then, well, okay, you look pretty normal. And so the number of cuts that it takes, or the number of kind of decision tree cuts it takes to isolate you, is inversely related to how weird you are. And so what you get is, for every single supernova, I get an anomaly score from this isolation forest. And I can also, because I have uncertainties on my latent space, I can also I can propagate those through just a Monte Carlo method, and I can also get uncertainties on that score, and that's what we do.
Okay.
Now for every supernova, I have a weirdness score and its uncertainty. Yep. And now we're just going to look at what we actually find using this.
Okay.
Yeah, and we can go to the next figure.
4.
Yeah, figure 4 is highlighting what we find. So this is an example of us now actually, less cartoony, actually doing it, where we have, like I said, I think it was 10 latent, I think it was 10 dimensional latent space. And these are just 2 representative subspaces of it. It doesn't really matter what kind of cut you take. I'm just saying, here's 2 of the, the model parameters I've learned. Yeah.
Okay.
And I'm showing all of the different classes. And then you can see that most of them want to cluster, and there are clearly a few that are outliers, and they're shown by stars. And in particular, these are ones where I'm making percentile cuts. I'm asking, okay, here's my list of anomaly score. I'll just convert that into a percentile. What's the top 1% doing, the top 0.1% doing, et cetera. And you can see right away that this algorithm favors some of these minority classes. So in particular, it really likes to pull out superluminous supernovae, which have the silliest name. So these are really bright supernovae, that are that we think are arising from newly born magnetars. In the plastic model, that is where they're coming from. And they are very rare. They are one of the rarest classes. They're pretty recently discovered. I think one of my fun examples I like though is that the rare classes we find now, we will find about 10,000 superluminous supernovae every year with LSST. Yeah. So even the rarest things won't be so uncommon. But you can also see it pull out a few other things. So there's a few 1As that have made it through, and the reason is often because they have bad photometric redshifts. Yeah, and then there's a few stripped envelope supernovae, 1BC. There's a parent stability supernova, etc. So we're pulling out some minority classes with some majority classes leaking in.
Okay. Cool.
Yeah.
Let me ask a question if you don't mind. I think you had mentioned in the beginning the idea that these were going to be real-time scans.
Yeah.
So curious how long this process takes to get to.
Oh, to run the code itself?
Yeah, from input data to
yeah,
potential anomaly detection.
Yeah, so it takes less than a second per object. It's really, really fast. And the reason why is because a neural network is just some matrix multiplications, and they're tiny matrices. Once it's done the hard work of learning or training the model, it has the set weights, and you're just asking it to, it's just a non-linear function.
Make those weights.
Exactly. So it's really fast, actually. Yeah. We can go to the next slide though and see that actually the limitation is the physics itself and not the model. And I'll explain what I mean by that. So this is a little confusing, but this is showing as a function of, on the upper plot, time relative to max, how much the anomaly score, the uncertainty of the anomaly score for many different events.
Yeah.
And you can see it's peaking around day 0. And the reason why this is happening is if you look at the second plot, which is showing the same data, but instead the x-axis is the number of observations. It's actually very uncertain until you have enough observations to really ground it in the model, to really understand what the model should be doing. So in other words, a different way of thinking about this is, as soon as it gets 3 data points, it's very uncertain because those 3 data points are really trying to anchor in that model, and there isn't enough power to do that.
Right.
Interestingly, when it has 1 data point, it does really well because it will default to the average. And so it just says, I don't know what this is. And so that's what's happening in the top, is that the vast majority of supernovae with very few points are at very high redshift. So we only detect them at peak. They just kind of blip up once and then they go away.
Yeah. Okay.
Yeah. And so we're actually, so the algorithm is not the limiting step. It is the several days it takes to get enough data to be confident and that it is anomalous and not be triggering on non-anomalous and highly uncertain things.
Good. Right. Makes perfect sense.
Yeah. We can go to the next figure, which is another big summary plot of this study. So like I said, we built an algorithm that didn't use the labels to figure out what was weird, but because we have the labels, we can check our answer and see if we did okay. And that's what this is doing. So this is a cumulative distribution for each of the different classes in plastic. And on the left-hand side, it means that that the objects are less anomalous to our algorithm. On the right-hand side, they're more anomalous. So if something is trending towards the left, like the 1As do, it's because they are less anomalous on average. And then you can see that something like the superluminous supernovae, which are this dark brown, they're kind of like take a while to go up, it's because the vast majority of them are being labeled as anomalous events. And so this is showing that our algorithm is doing what we expect it to do. If we actually break down by the classes, the things which are rare, so the intermediate luminosity, the kilonovae, the superluminous supernovae, are being marked as rare. And the more common things like the 1A and its subtypes are less anomalous on average.
Okay.
Okay.
good.
And then we can go to the next.
Good. Okay. Fig 7, results and discussion.
Yeah, we
Okay.
we checked for a lot of systematics. So
Yes.
So this is now asking, so what's going to happen in reality? In reality, we're going to get all of these different supernovae coming in, and we're only going to be able to look at the top few percent, really. And so this is asking if I make cuts on the anomaly scores, just to get a realistic sample that we could actually look at in real time, what's that going to look like using this algorithm? And so this is showing a few different cuts. So I'll just talk about the leftmost one.
Okay.
And so A represents the anomaly score, and it's asking, am I in the kind of the 5% most anomalous of all the sample? And I want my uncertainty to be less than 1%.
Right.
Where the uncertainty can, again, it can come from the anomaly score kind of latent space itself, but it also comes from things that were simulated like photometric redshift, which was a huge issue for us. So the photometric redshift was as realistically as possible simulated, and if it was highly uncertain, it led to a highly uncertain anomaly score. So if we do that, the top panel is showing us the breakdown of the remaining sample.
Okay.
And most of them, so like the top left we can look at, in this case for just this cut, most of them are superluminous supernovae. So they are a minority class.
Yep.
Then they're followed up with the two majority classes, 1As and type 2s, and then followed by a very rare class, pair instability supernovae, which are these, some would say theoretical still, some would say observed classes of core clump supernovae.
Depends who you talk to there, but yes.
Yeah, exactly. So we do have contaminants, but if you look at the plot on the left-hand side, under this plot, you're showing the abundance, which is a way of saying how over or underrepresented are these different classes.
Yeah.
So you can see that superluminous and peri-instability supernovae are overrepresented in our sample. So we're very good at over-selecting them by about a factor of tens. I don't know what this is, like 50 or something. Yeah. Whereas we are, although there are a lot of contaminants, the 1A and type 2 are heavily underrepresented. We are about, again, a factor of 10. So we are weeding out a lot of them, but again, there are just so many of them that it's really hard to get rid of every single one. And in particular, the ones that we are holding on to, so like the 1A that makes it through these cuts, it's because it's not only the photometric redshift was uncertain, it's actually a catastrophic failure, which means that it had a low uncertainty, but it was absolutely incorrect redshift. And so it might turn a normal 1A into something that looks really bright, like a superluminous supernova. And so this was really the issue. And so one of the key findings for us was the fact that we really need realistic error estimates on photometric redshifts for LSST. So it was very helpful that Plastic had simulated this. It was a good wake-up call to how important that is.
Yes.
And then we can go to the next. I think will be the final plot.
Okay. Ooh, vector plot. Okay.
Which is yeah.
Flow diagram.
So there's two, or no, I'm sorry, it's one figure, two plots. These are, I lovingly refer to the one on the right as the worst plot I've made because it's it's hard to, it looks ugly, but I'll explain it. So first on the left-hand side, part of the whole selling point of this was that it was a live anomaly detection. We wanted to, in real time, know whether or not something was anomalous. And so it's really important that we're able to trigger on these things early so that we can get multi-wavelength follow-up and actually know what the physics are.
Right.
So this is showing, both of these are showing in different ways. How does the anomaly score change as a function of time? Okay. On the left-hand side, it's kind of this aggregate view. So it's a 2D histogram, which is what the shaded blocks are showing. They're just saying, okay, on average, what is kind of the anomaly scores of the different supernovae as a function of time. And then the vector plot is showing you how does that anomaly score change as a function of time. Yes. And what's really key is that around and after peak, it doesn't change.
Yeah.
It has basically settled into knowing if it's an anomaly or not an anomaly by then.
Wow.
So this is really important because if you wanted to, just the most naive optimization for follow-up is to get it at peak because it's cheapest to observe then.
Yes.
You also want to do it ideally pre-peak in many cases because there are many additional really interesting physical phenomena that can happen before peak.
Yes.
So it's important that we grab them. And that's what the plot on the right is highlighting.
Okay.
So this is saying for a selection of different supernovae, so every curve represents one supernova.
Okay.
And it's asking, is this supernova part of all of them were labeled as anomalies.
Okay.
We're ignoring the gray. And they're all labeled as anomalies because they go over this green line. So at some point in their light curve, they reach an anomaly percentile score that's high enough that we trigger on them.
Okay.
The question is though, I have the majority class, so type 1As, contaminating my sample of real anomalies, things from minority classes. When do the majority and minority classes get labeled as anomalous?
Okay.
The blue curves are true anomalies. They are minority class, interesting physics. We want to trigger on them. In general, those will be identified as anomalous before they reach peak with this algorithm. So we trigger on them early.
Nice.
The 1As, which are the orangish lines, which are like the fake anomalies, are triggered after peak and like a week or so after peak. And so actually this is really helpful because we most likely wouldn't follow these up because we can, A, we've missed peak, so they're not optimal, and B, we're more likely to be able to say, I can just fit this to a 1A model and see that it's likely a 1A at the wrong redshift. And so this was very helpful in understanding the algorithm is able to generate an anomaly score over time. That anomaly score is not a random number. It stops evolving and kind of it converges to a single value around peak. And even though we have contamination in our sample, the contaminants typically show up after peak. So we are still likely to trigger multi-wavelength follow-up on real anomalies before peak.
Yep, that's the here.
Yeah, exactly.
They don't really have an anomaly score of 1.2. They're just pointing out.
No, they're just pointing out the time at which they get triggered.
Exactly. Okay, good.
Yeah. I think that's everything that I want to say. Yeah, so I think now what remains to be seen. So like I said, this is all simulated data, and there is definitely a difference between simulations and reality. And
no way.
Yeah. And I think you never quite know what the universe will do in reality.
Yeah.
So it certainly remains to be seen how this can be translated into a real survey. It runs in real time. There's not a computational limit. It's just a matter of actually plugging it into data.
Okay, cool.
Yeah.
So first, thank you very much for walking us through this very lovely APJ sub-article. Very nice. You hinted at it there at the end.
Yeah.
And so let me just follow up a little bit on that, I guess on two fronts. I mean, there are real data streams. ZTF, for example.
Yes.
You could pump this through some real data sets prior to Vera Rubin. So that's question number one. And question number two is and it's related, is where do we take this in the future? Are there other data sets that can be plugged in? Are there different, perhaps different neural networks or machine learning algorithms that might do a better job of doing anomaly detection and that kind of stuff? So just kind of, where do we head over the next 5 years or so?
Yeah, I think first, so immediate kind of goals. Yeah, obvious, there's data that exists. ZTF is the best candidate. So we are working on, actually not for exactly this algorithm, but I'm working with some students on a very similar algorithm for variable stars. And I think in general, anomaly, which are from, sorry, the ZTF catalog. I think in general, anomaly detection is really growing as a field. And the reason why is because we just have so much data and we can start asking these interesting rare physics questions.
Yeah.
And so there is a huge need to implement these in a very public facing way. So this type of anomaly detection, so that the community can actively use it. So I am exploring putting this into what are called, there's a whole political sphere here, but the broker systems of LSST,
Yes,
which
yes.
is just,
Yeah, we won't
just
go there too much, but I know what you're meaning.
yeah, it's just a, I don't have to explain all this jargon, but it's just a way that that the community can use it, and
Right.
everyone can use this with open data. So that definitely needs to be done, and these brokers actively currently serve ZTF data. ZTF data is very different than LSST data, so it's not exactly, it's not just plug and play. It would have to be retrained for ZTF data, but that's doable.
Yes, yes.
And then I think looking forward, machine learning is growing so rapidly and changing. And like I said, anomaly detection's also a big field in machine learning too. And so I'm very hopeful that algorithms continue to mature. And I think one thing that would be really exciting is, so all of this is physics agnostic, and that was in many ways on purpose, but it'd be interesting to know if you can combine these with physical models and actually actively get interpretations of the data as they come out, while also looking for these weird needles at the same time. So all of this infrastructure still needs to be built really before LSST, and the community is working very hard to do so. But I think it'll be really fun once it comes online.
Very cool.
I think there'll be many discoveries. Yeah.
Yeah, very cool. Just to pick up on one aspect of that, I mean, so for example, while 1As might be boring, we still, just to pile on to what you're saying, we still don't know what the progenitor system is.
It's true. Yeah.
More likely progenitor systems, and they could have very different physics mechanisms to get to the 1A. And so using sort of this to pull those out would be very cool.
Yeah, absolutely. I think all of it's very fun that one person's, I don't want to call it trash, but our contaminant is someone else's treasure, and we have to work together. We have to work together both for just all the physics is intimately connected, but also in that we will clean up each other's samples if we really know how to identify the two. Yeah.
That was a lovely analogy, I have to say.
Yeah.
You did really well with that. That was great.
Yeah.
Very cool. All right, Ashley, thank you once again. And thank you everyone for listening in. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.
Bye.